In this lesson, we're just going to look at some examples, if you like, using electric fields. The first we're going to look at is Millikan's famous experiment to work out the charge on an electron, and then we're going to look at deflection in an electric field. First up, then, this is Millikan, and what he did, he was able to calculate the charge on an electron, and he did this via using electric fields to support oil drops. This is a diagram of his experiment. You don't really have to know it inside and out, but you never know with exam questions if they ask you about this. It's nice to have seen it. Basically, he used air came through this thing called an atomizer, which basically made the oil drops, made the oil into very, very small drops. They were fairly regular sized, and the oil drops came down this tube, and they began to fall under gravity through this metal plate, and there was only a small hole to allow them to fall just in one place. This was a known width, and there was an electric field across this. You can see here that this was connected to a supply, and there was an electric field across this gap. So we've got a uniform electric field. So they were falling under gravity. What he had to do, we needed to get these charged. So the way he got them charged was he charged them by having X-rays coming through, and that meant that they were attracted to the top plate. So they were falling under gravity, but they were also attracted to the top plate. And basically, he adjusted the electric charge, the electric field between the plates, so that eventually the little drops of oil remained stationary or became suspended between the two plates. Now, at this point, he knew that the force from the electric field was equal to EQ, and he got a value for the electric field based on the distance between the plate and the voltage. Obviously, he's looking for Q, but he also knew that the oil drops were going to fall under gravity, where weight equals mg. Weight being the force, when the oil drops were suspended, he knew that W equals F, so he put these two equations together and got EQ equals mg, and rearrange that to give the charge would be the mass times the gravity divided by the electric field. So he did this, and he found that the results that he got, the Q that he got, was always a multiple of a particular constant. He had to repeat this a lot of times to work this out, because obviously he ended up with more than one electron on the oil drops. But he noticed that the charge on each of these oil drops was always a multiple of a particular constant, and this constant was 1.6 times 10 to the minus 19, and hence he found the charge on an electron. Okay, another little example here. This is quite a classic style exam question. You've got an electron travelling at 3 times 10 to the 7, enters the electric field between two parallel plates here. There's a potential difference of 400 volts and a separation of 4 centimetres, and the parallel plates last for 10 centimetres. So what's going to happen is the electron is going to be attracted towards the positive plate, so it's going to accelerate upwards towards the plate. It's going at a constant speed through, so its horizontal velocity is constant, but as it comes through the plates, it's going to accelerate upwards. We've got some calculations to do. The field strength, the force on the electron, the acceleration of the electron, the time to pass through the field, and the magnitude of the velocity and the angle of the path once it leaves the plates. Okay, if we go through it step by step. Field strength between the plates, easy calculation, E equals V over D, 400 volts, 4 centimetres, gives us 10,000 volts per metre. The force on the electron, here we can use F equals EQ. We know the electric field because we've just calculated it. We know the charge on an electron, 1.6 times 10 to the minus 19 coulombs. So we can get a force on the electron as 1.6 times 10 to the minus 15 newtons. The acceleration, we can use Newton's second law here because we've got a mass. We know the mass of an electron. We know the force on an electron, so we can use F equals ma. If we rearrange that to A equals F over m, we insert our force and mass, and we come up with an acceleration of 1.76 times 10 to the 15 metres per second. The time for the electron to pass through the field. We do know the distance because the plates were, I think they were 10 centimetres long, so we can use time is displacement divided by velocity because we are given the velocity. It is 10 centimetres, that's 0.1 metres. The velocity of the electron was 3 times 10 to the 7 metres per second, so from that we know that it is between those plates for 3.33 times 10 to the minus 9 seconds. So obviously because it's going at 3 times 10 to the 7, it doesn't stop between those plates for very long. Okay, the harder bit, I suppose, is question E. What's the magnitude of velocity after leaving the plates? Well, we know that in its velocity in the y direction, we've got an acceleration upwards, which we've just calculated, and we know it's going to be accelerating upwards for the time that it is between the plates. So it was accelerating at 1.76 times 10 to the 15, and we know it's between the plates for 3.33 times 10 to the minus 9 seconds. So its final velocity in the y direction, we can shove that in our calculator and we get 5.86 times 10 to the 6 metres per second. So this is in the y direction, but we've also got a velocity in the x direction because it's coming in at 3 times 10 to the 7 metres per second in the x direction. So we've got to do some mechanics here, because we know the velocity in the x direction, we know the velocity in the y direction, and we want to find the resultant velocity. So I'm just going to use a bit of Pythag. That VR, this side of the triangle, will be the resultant velocity. So VR equals Vy squared plus Vx squared. If we put our numbers in, this is what we've just calculated up here, the velocity in the y direction. This is velocity in the x direction. If we work all that out, we know we get a final resultant velocity of 3.06 times 10 to the 7. So it's going slightly faster than when it came in because it's been accelerated as well in the vertical direction. Finally, the angle of the path. Well, here again we can use some Pythag. We can say that the tan of this angle here, tan of this angle theta, is opposite divided by adjacent. I've got opposite as Vy and I've got adjacent as Vx. So if I just put in 5.86 times 10 to the 6 divided by 3 times 10 to the 7, which is Vx, work all that out, do an inverse tan, and I get a tan of 11.05 degrees.